Welcome to CivilizationX. Blood sugar changes continuously. Human treatment is delayed, intermittent, and forced to correct a system the pancreas normally controls in real time. In 2021, 537 million adults aged 20 to 79 were living with diabetes worldwide. The International Diabetes Federation projects 643 million by 2030 and 783 million by 2045. In the United States, 38.4 million people had diabetes in 2021, including 8.7 million adults who met laboratory criteria but were undiagnosed. Global health expenditure reached $966 billion. AI is entering the system at distinct points. Glucose prediction in continuous monitors and pumps, retinal image triage in clinics, risk detection in records, and drug design at firms such as Isomorphic Labs with Eli Lilly and Novartis. The claim is precise. AI improves diabetes control, screening, and discovery pipelines. But that is not the same as curing the disease. A healthy pancreas samples blood glucose continuously and releases insulin within seconds into the portal circulation. Diabetes breaks that control loop. In type 1, autoimmune destruction removes beta cells. In type 2, insulin resistance, liver glucose output, muscle uptake, adiposity, sleep, diet, and activity distort the response. Subcutaneous insulin is slower than native insulin, and interstitial glucose sensors lag behind blood glucose. DCCT and EDIC showed that tighter glucose control reduces long-term complications in type 1 diabetes. The problem is not knowing control matters. The problem is maintaining near-normal glucose manually, hour after hour. That is where algorithmic control started to matter. In September 2016, the FDA authorized Medtronic's MiniMed 670G, the first autonomous insulin dosing system for people with type 1 diabetes aged 14 and older. As Jeffrey Shuren put it, the system automatically monitors glucose and delivers appropriate basal insulin doses through the pump. The mechanics are concrete. A continuous glucose monitor streams readings about every 5 minutes. Software forecasts the trajectory, and the pump adjusts basal insulin before the next excursion fully unfolds. In a 2019 New England Journal of Medicine randomized trial, Tandem's Control-IQ raised time in range from 61% to 71% over 6 months. As Boris Kovachev and colleagues reported, closed-loop use produced more time in target than sensor-augmented pump therapy. Insulet's 2021 Omnipod 5 pivotal trial added 2.2 hours per day in range for children aged 6 to 13.9 years, and 2.9 hours for participants aged 14 to 70. A separate AI domain is complication screening. Google researchers reported in Nature in 2016 that deep learning detected diabetic retinopathy in fundus photographs with AUC values of 0.991 and 0.990. Varun Gulshan and co-authors showed image data could be triaged at high sensitivity and specificity. In 2018, IDXDR, now Luminetics Core, became the first FDA-authorized autonomous AI diagnostic system for diabetic retinopathy in primary care. So, can AI cure diabetes? No. For type 1, closed-loop systems optimize external insulin, but do not stop autoimmune beta cell loss. For type 2, algorithms can personalize care, but remission often depends on weight loss, surgery, or drugs such as GLP-1 and dual agonists. Screening has limits too. If a tool with 99% specificity is used where retinopathy prevalence is 1%, 1 million screenings produce about 10,000 false positives, alongside roughly 10,000 true positives. Accuracy alone does not determine clinical value. The next 5 to 15 years are about anticipation, not reaction. Multi-sensor closed loops, better insulin delivery kinetics, digital metabolic models, and AI-guided drug discovery. In 2024, Isomorphic Labs partnered with Eli Lilly and Novartis because better molecules and immune-modifying therapies are still required. The constraint is real. The data exists. Whether the systems built around it can act on it at scale, that is the next engineering problem. Stay with Civilization X.